In the last class, we were discussing about the flame, that is the absorption cell it is called technically, but actually it is a space in the where flame comes in the optical path of the hollow cathode radiation. So, I had shown you this figure where I had shown you that there are primary combustion zone, internal region, secondary combustion zone, etc. This I had explained to you, and the temperature variations of this flame, we have seen that the optimum temperature is somewhere around around about 2 to 3 meters height from the origin of the flame, and it extends this 1860 range temperature extends from about 0.5 to 0.5 centimeter on the left and right of the flame. So, we have also said that the optimum temperature for the production of vapor phase atoms are different. So, I had shown you this figure, for example, chromium, the optimum frame is optimum height is it should be as near the flame as possible, but for magnesium there is an optimum somewhere around 2 centimeters, and so for silver it is about 2 maybe about 3 to 3.5 centimeters. I had also explained to you that the height of the flame can be adjusted in almost all instruments to get the optimum response of the signal. Okay. Now, air acetylene we had discussed. The flame air acetylene is the most common flame used in atomic absorption spectrometer, and this flame is completely transparent above 230 nanometers, but shows about 65% absorption around 193.7 nanometers. So, normal temperatures of about 2400 degrees are obtained using air acetylene flame depending upon the flow rate of the gas and oxidizer. So, this is quite sufficient for the atomization of the most of elements except refractory elements. So, alkali metals, sodium, cesium, potassium, etc., they do ionize to an appreciable extent if I put it in the flame, that is air acetylene flame. If you remember your high school chemistry or PU college chemistry, you will remember that there is a test for the determination of sodium by putting it in the flame. You will see yellow flame. Why does it happen? Because most of the atoms, free atoms are produced, they emit the radiation corresponding to different colors, and that is one of the qualitative method for the determination of sodium, potassium, etc. That is also known as borax bead test also sometimes. So, alkali metals we know that they do ionize to an appreciable extent even around 2000 degrees centigrade. So, if they ionize, we have not much use of the metal because we want free atoms. Ions do not absorb radiation, but free atoms do absorb radiation. So, that means ions must pick up electrons to become atoms. That is what happens in the flame, because in the flame there are a lot of free electrons moving around, and whenever I put an ion, it must pick up the electron to form a metal atom that is in the ground state. So, this flame is alkali metals normally ionize quite a lot, and therefore, alkali metals are not used for atomic absorption spectrometry are not determined using atomic absorption spectrometry 99% of the time. We have other techniques for that. So, continuing this discussion, what we want to say is this flame air acetylene is operated under stoichiometric conditions or weakly oxidizing conditions, that means excess air for gold, iridium, palladium, platinum and rhodium. So, alkaline earth metals are determined in a slightly reducing flame, that is excess of fuel gas, that is green or blue flame, because these are the temperatures lower than the optimum temperature, but it is quite sufficient for alkaline earth metals. Now, I had explained to you that there are air acetylene is one of the combinations, but I had also shown you that nitrogen oxide, nitrous oxide and acetylene is another gas mixture which will give you temperature of about 3000 degree Kelvin centigrade. Okay. Now, we make use of this system also in flame atomic absorption spectrometers. That means, whenever you buy an atomic absorption, people normally buy air acetylene, that is acetylene cylinders, and also nitrous oxide cylinders. Okay. So, the advantage when I use nitrous oxide is it can give me a temperatures of about 3000 degree Kelvin. Look at the next slide now. So, an important development in atomic absorption spectrometry is the introduction of nitrous oxide and acetylene combination. This flame is operated with a slight excess of fuel gas, that means the flame would be red color. So, you have to adjust it in such a adjust the flow rate of nitrous oxide and acetylene to get a reddish flame, and this flame has a 2 to 4 millimeter high blue zone, blue white primary zone, above which 5 to 50 millimeter, that means almost 5 centimeter red reducing zone is present. So, the red flame is the reducing flame. So, if you use this, most of the oxides can be reduced to metals, but these oxides belong to refractory elements. So, the red reducing zone is suitable for the analysis of refractive elements such as molybdenum, tungsten, vanadium, chromium and several rare earth elements, and this is largely free from interferences. That is the beauty of this nitrous oxide acetylene flame. So, the burning fuel produces carbon monoxide environment according to this reaction, that is nitrous oxide will react with acetylene to produce carbon monoxide, which is a reducing agent, and then there are other products are nitrogen and water. So, all these things will be in the gaseous state whenever you are operating an nitrous oxide acetylene flame. So, nitrous oxide acetylene flame has two disadvantages also. What are the disadvantages? Due to high temperatures, that is almost 2500 to 2800 degrees, appreciable ionization occurs for many other elements than your analyte. So, the that results in reduced sensitivity. That means, the other elements do if you want to determine using nitrous oxide, you will not get the high sensitivity. Secondly, the flame also emits strong broadband emissions of cyanide, CH and NH bands. That means, these are molecular absorption bands corresponding to carbon nitrogen combination in the air. So, it forms a cyanogen radical, and then we also have carbon hydrogen combination CH and NH. All these bands have very short lifetime, okay. But these bands do have a strong absorption band just like spectrophotometer. It is a broad band, it is not a very sharp band. Unlike atomic absorption, what we are talking here, because it is a resonance line and the requirement for atomic absorption is 0.002 nanometers. But if in the flame there is a broadband absorption, so part of it will contribute to the will correspond to the atomic resonance line also. So, but it is not due to the element. So, this introduces a little bit of error due to their contribution to the analytical resonance line. It also introduces emission noise, because noise is nothing but additional signal that is picked up at the detector level. So, this can affect the precision of the analysis, because noise is not exactly same all the time. So, noise can vary. So, the signal also will vary. So, therefore, the emission noise is not desirable. Okay. So, I was telling you that this broadband, I want to make it a little more clearer by drawing this figure. What is important is I have an absorption signal. This is absorbance. Okay. This is my wavelength. An atomic absorption signal is a very sharp signal. Now, this is the broadband signal for CH. It is also similar, it may be somewhat similar for other NH ions. Similar broadband signals are there for cyanide NH bands. So, now what I am saying, there is a possibility of combining carbon atoms and hydrogen atoms to form a CH radical, or it may be a CH molecule also. Similarly, CN is possible, carbon nitrogen, cyanogen it is called, and then NH is called amine or something like that. Now, consider my resonance line would be something like this. Okay, this is my resonance line. For AAS. For atomic absorption, I have a resonance line. So, what happens if I am measuring absorbance at lambda, I will also be measuring additional absorbance of the broadbands. Okay. So, what is the additional absorbance I am going to measure? This is the additional absorbance this is the additional absorbance I am measuring at lambda, but it is not due to the element which I want to determine. So, this introduces a noise or an electrical noise which is not wanted. Therefore, what I should be measuring? I should be measuring an additional, I want to measure only the resonance line, but this is the additional information that I am getting, because this portion also belongs to this absorbance is a combination of the AAS absorbance plus the broadband contribution. I think you are convinced of the problem here, because all these broadbands have some amount of absorbance. The system cannot differentiate between the resonance line and the absorbance of the CH, NH and other bands at the resonance line. So, the total absorbance would be the algebraic sum of the signals at the resonance wavelength. Okay. So, in addition to the composition of the gas mixtures, their burning velocities are also important. If the gas flow rate does not exceed the burning velocity, the flame propagates back into the burner, giving a flashback. So, what is a flashback? The flame will get sucked and then there will be an explosion. So, we should be very careful whenever we want to determine any element using atomic absorption, because we do not want flashbacks and explosions occurring in the burner. So, at high flow rates, what happens? If the high flow rates, generally the absorbance, that is the fuel gas is more, okay, and eventually it reaches a point where it blows out of the burner. There are instances where the whole burner itself is blown off. Therefore, it is very important to adjust the flow rate of the fuel oxidant mixture until it reaches a point above the burner where flow velocity and burning velocity are equal. Both flow velocity and burning velocity should be equal. So, now we move on to another aspect of atomic absorption, and that is to understand what exactly happens in an atomic absorption process. That is, we have already said negative, we have already said there is a need for nebulization, and from the nebulization we want the free atoms in the space where flame is burning. So, we are introducing the sample in the form of vapor. So, what is the mechanism of atomic atomization? So, how does it happen? So, there are several theories, and the most popular mechanism normally involves the desolvation, that is there is a desolvation process and volatilization process, dissociation process and excitation process. So, what we are saying is, whenever we introduce vapor atomic solution into the atmosphere of the flame, the droplets that are being produced will normally have to undergo evaporation. So, the different steps are, first it must be desolvated. There is almost every salt is having some amount of solvation water molecules around the ions. So, those water molecules should be removed, that is desolvation, and then once the water molecules are gone, then we want the atoms, the water droplets to volatilize. So, after it volatilizes, all the liquid is removed, what will remain? The metal salt in the solid form. That solid form of the metal in the flame should be, it undergoes dissociation, and once the dissociation is complete, ions will be forming, and these ions will take up electrons and get excited to higher energy level, etc., free atoms, etc., and then we will have atomic absorption. So, with so many processes occurring, it is not surprising that the atomization is the most critical step in the flame atomic absorption spectrometry, which determines the sensitivity and precision of an analysis. So, this is the process. Here what I have is a solution. Suppose I want to determine copper, then I will have Mx, copper chloride. Okay. So, copper Mx, what we mean is, it is a copper chloride solution. So, the moment I put it in nebulization, whenever I have this Mx solution, I put it through the nebulization, and in the nebulization what is produced is aerosol. This aerosol is what is the aerosol composition? It is the Mx, that is copper chloride. I am only taking the example of copper chloride, but it can be any salt. So, I have Mx solution aerosol. So, part of bigger droplets condense and then get discarded here in this range. Okay. Now, smaller droplets, what happens? They undergo solvent evaporation, that is desolvation, and then Mx, that is copper chloride, solid aerosol will be there. That means, just like talcum powder in the air, whenever you press it, so the solid powders will be formed, and these solid aerosol particles of copper chloride will continue to volatilize, and Mx gaseous, next step is gaseous formation, gas vapor formation of the copper chloride. Okay. So, I have written here Mxg into bracket. So, this Mxg gaseous form of the copper chloride can take up an electron, go to next higher energy level. I denote this as Mx star. That means, it has picked up an electron there, and this excited electron can be lost by emission, and again it forms the Mx gaseous. That means, there is an equilibrium reaction between the Mxg and Mx star. Okay. That is one side reaction which does not contribute to the atomic absorption. Okay. Now, this Mxg, two aerosols of Mx gaseous can combine to form association products, and or it may undergo dissociation also, because temperature is very high in the flame. So, this dissociation produces Mg, that is metal vapor in the gaseous form. Okay. In this form, again it can pick up electrons, or it can undergo chemical reaction with oxygen, hydrogen, etc., in the flame. Okay. So, if it undergoes chemical reactions with the flame elements, I have MO, metal oxide, and metal hydrogen, metal hydride, MOH, that is metal hydroxide, etc., and these things can also be dissociating to form Mg, that is metal vapor. That means, this is another side reaction where there is loss of metal ions to some extent. And then another way of losing is they undergo ionization M plus E minus. This is again an equilibrium reaction, and they can combine, M plus and E minus can combine to give you metal gases also, gaseous metal in the gaseous form. Okay. Now, this molecular orbitals, molecular compounds, excited molecular compound can get excited to higher energy level and emission. So, there is molecular excitation and emission process occurring in the flame for MO, MOH, MH, etc. So, this is again another equilibrium reaction which does not contribute to the atomic absorption measurement. Now, similarly, the metal ions, if it undergoes excitation, there is not much atomic absorption here. Now, the other process is this metal in the gaseous form can undergo form atoms, and this atom can get excited, and there will be an equilibrium between excited and non-excited metals, and it may lead to atomic absorption or it may lead to atomic emission depending upon the temperature and property of the element. So, among the emission is this fluorescence emission spectrometry and atomic fluorescence spectrometry, both are possible, and instruments are available to measure the atomic fluorescence and this flame emission. But right now we are talking about atomic absorption spectrometry, that is we are interested only in this process. Okay. So, this is how the mechanism of atomic absorption takes place. So, this I have already explained to you that atomization step converts the analyte within the aerosol into the free ground state atoms. Several processes I have already described. I think you are comfortable with the presentation.